This is part 6 of second lecture of week 9, and this is the final part of this lecture where we discuss the third thing that you may get using the method of partial fractions. You may get quadratic factors in the denominator. What does it mean? It means that your function can be, say, some polynomial in numerator, and in the denominator you may have, say, s minus alpha squared plus beta squared, something like this. In this case, the fraction corresponding to this factor is the following. Let's say cs plus d over s minus alpha squared plus beta squared, plus, and maybe some fractions for other factors. And you can see that if we write this in this form, we will use this formula and this formula to calculate the inverse Laplace transform. And here you can see that the numerators in the form b and c minus a, so it's not in this form. So it's better maybe to find the numerator here in the form a s minus 1 minus alpha plus b beta over s minus alpha squared plus beta squared. So we immediately show, if we find this in this form, we will show that a is the number of sines, of cosines in the formula, and b is the number of sines in the formula. So after we do this, so a and b are numbers that we need to find. Then the inverse Laplace transform of the function f at a point t will be something, and corresponding to this particular fraction, this will be a times e to the alpha t. For a, this is cosine beta t plus b e to the alpha t sine beta t, and plus maybe some other transforms. Okay, let's look at an example. So for example, we're given this fraction here, and you can notice if this is function f of s, we can write this function as 2s squared plus 10s over this bracket here is the same as s minus 1 squared plus 4, right, which is 2 squared times s plus 1. So it's better if we write it as a times s minus 1 plus 2b over s minus 1 squared plus 2 squared, and plus the fraction for s plus 1, so like this. So this first fraction is corresponding to this factor, this second fraction corresponding to this factor here. So let's find a and b. Let's use again the second method. So we multiply everything by the denominator. So what we get, 2s squared plus 10s is equal to a s minus 1 plus 2b times s plus 1 plus c times s minus 1 squared plus 2 squared. So we obtain this expression, and let's take some values of c. Let's take s to be minus 1. In this case, the left hand side is 2 minus 10, which is minus 8. And this a and b bracket will be 0 because of this s plus 1. And for c, what do we have? If s is minus 1, we get minus 2 squared is 4 plus 4, so this is 8c. So c now is minus 1. Okay, to find a and b, we need some other values. Let's take maybe s to be 1 to make it simpler, If s is 1, the left hand side is 12. This coefficient of a is 0, coefficient of b is 4, and coefficient of c is, this part is 0 for c, or 12 is for b, and for c we already know the value, minus 4. So 16 is for b, so b is 4. And now it's left to find a. Let's take maybe s to be 0 to make it simple. So we get 0 is minus a plus 2b. And here we get 1, so 5c, right? 5c, it's 1 plus 4, which is 5. So 0 is minus a, b is 4, so plus 8, and minus 5. So we will obtain a is 3. So now f of s is a is 3, s minus 1, and b is 4 plus 2 times 4 over s minus 1 squared plus 2 squared plus, it's minus c is minus 1, so it's minus 1 over s plus 1. So therefore the inverse Laplace transform of the function f at a point t is equal to, so we have 3 times s minus 1. Here we'll use the formula for cosine. So alpha a is 1 here and b is 2. So we get e to the t cosine 2t, right? b is 2, s is 1, a is 1. And this part here we obtain 4. For b, we will use this formula. For b is 2, so plus, okay, I forgot 3 here, sorry, plus 4 e to the t sine 2t, and also minus this fraction. For this fraction we use this formula, e to the minus t, so minus e to the minus t. So this is the answer for this particular example.